Question number 36. Consider the following circuit breakers for 220 kV substations, air, SF6 and vacuum. Which of the following circuit breakers can be used in an indoor substation? Option A 1, 2 and 3. Option B 1 only. Option C 2 only. Option D 3 only. Now what is the voltage level here? It is 220 kV. Now we know that for 220 kV we can use SF6 circuit breaker. Out of these three, air circuit breaker usually it is restricted only up to 11 kV. Vacuum circuit breaker it is used only up to 33 kV. SF6 circuit breaker it can be used from 11 kV till the highest transmission voltage level, it is 765 kV. So here correct option it will be SF6, that is option C, 2 only. Now in indoor substation, the example we can consider one of the example of indoor substation as gas insulated substation, GIS. Now in case of gas insulated substation, entire switchgear equipments they are kept in a kind of enclosure which is filled with a gas which is SF6. So here correct answer it will be option C. The question is asked in ESE exam 2016. Next, question number 37. A power system with two generators is shown in the figure below. The system, that is generators, buses and transmission lines, is protected by 6 overcurrent relays R1 to R6. Assuming a mix of directional and non-directional relays at appropriate locations, the remote backup relays for R4 are. So here this is our relay for which we need to determine which will be the remote backup relay. We know that there are two types of backup relays. One is the local backup. So if we write here, so backup relays are of two types. One is local backup, another is remote backup. Now what's difference between these two? As the name itself suggests, local means the location of this backup relay is near to the relay under consideration, whereas remote backup means it is located at a remote location. Now here we are asked to find the remote backup for relay R4. Now for R4, the remote backup which are away from this, that will provide the backup protection in case R4 does not operate, this relay will operate. So it will be R3 as it is in the remote location, then R1 and R6. So here remote backup for R4 it will be R3, R1 and R6. What about local backup? Now at the same bus bar near to this relay R4 we have R2 and R5. So this R2 and R5 they will provide the local backup. Now out of these four options, in which option R3, R1 or R6 is mentioned? So here it is R1, R2 which is not correct, R2, R6 which is also not correct, R2, R5 that is not correct, R1 and R6. So this option is correct. So correct answer it will be R1, R6. This question is asked in GATE exam year 2016. Question number 38. The steady state stability limit of a synchronous machine connected to infinite bus is 2.2 per unit. Infinite bus voltage is 1 per unit and synchronous machine's voltage is 1.1 per unit. The transfer reactance between generator and infinite bus is. So here we have a generator. This generator is connected to an infinite bus. So infinite bus is that bus which will maintain the voltage and frequency irrespective of how much amount of power is injected or taken from that particular bus. So this is our infinite bus. This is the generator. This is the transfer reactance. Now we have given the steady state stability limit as 2.2 per unit. Infinite bus voltage. Now let us call this voltage, let us say E. This voltage of infinite bus, let us say it is V. The infinite bus voltage V is 1 per unit and synchronous machine voltage, that is E, is 1.1 per unit. we have to find how much is the transfer reactance. That is, this reactance X equal to question mark. This question is asked in ESE year 2013. Now we know that steady state stability limit is given by EV by X. So from where we have got this? So we know the power transferred from generator to the infinite bus, it is given by P equal to EV by X sin delta, and when this power is maximum, that particular limit is known as steady state stability limit, and it will occur when delta is 90 degree. So if you put sin delta 90 degrees, so sin 90 will be 1, and this term is nothing but steady state stability limit. Now using this particular equation, steady state stability limit, we need to calculate X. So X will be equal to EV upon steady state stability limit. So value of E is 1.1, V is 1, and limit stability limit is 2.2. So from this X will be 1.1 by 2.2, that is half, which is nothing but 0.5 per unit. So correct answer, it will be 0.5. Now as it is a reactance, we know reactance is always J times. Therefore correct answer, it will be option A. Question number 39. For a single line to ground fault, the terminal conditions are, 4 options are given. Now we know that if this is our 3-phase system, 3 transmission lines R, Y and B, as a standard convention, whenever SLG fault is there, we assume that that fault occurs on phase R. So if we indicate the fault on phase R, we can assume some fault impedance. This point is connected to ground. So this is the fault impedance ZF. In case of dead short circuit or solid fault or bolted fault, ZF will be 0. Now this is the situation for single line to ground fault. Now in this case, the maximum current or the fault current, it will be through phase R only. Now whenever we do the fault analysis, the pre-fault current or normal load current is assumed to be 0. So if we write IY, so IY will be 0, IB it will be equal to 0. And as I told, if ZF is 0, that is a dead short circuit, then this point is directly connected to the ground. In that case, the voltage of that phase, it will be 0. But practically we know that fault path will have some impedance. So that's why we are indicating ZF. Here if ZF is 0, VR is 0. So our conditions will be VR equal to 0 and IY equal to IB equal to 0. So this is the terminal conditions for SLG fault. Now here notations are given in terms of ABC. So we can write VA equal to 0 and IB equal to IC equal to 0. Correct answer, it will be option A. Question number 40. A 25 MVA 33 kV transformer has a per unit impedance of 0.9. The per unit impedance at a new base of 50 MVA at 11 kV would be 10.4, 12.2, 14.4, 16.2. Now we should remember the equation of per unit impedance referred to new base. So Z per unit new will be equal to Z per unit old into SB new by SB old into VB old by VB new whole square. So what is Z per unit new? Per unit value of impedance referred to new base quantities. Z per unit old, per unit impedance referred to old base quantities. SB new is base MVA new, SB old is base MVA old, VB old is base voltage old, VB new is base voltage new. So this formula we need to use here. So how much is Z per unit old? They have given that initial or original per unit impedance is 0.9. So here we can write 0.9 into new SB, that is 50 MVA divided by old SB, that is 25, into VB old, that is 33, upon VB new, that is 11 whole square. So 25 2s are 50, 11 3s are 33. So that will be equal to 0.9 into 2 into 3 square, it will be 9. So 81 into 2, it will be 162. So decimal point 16.2 per unit. So if original impedance is 0.9 per unit at these base values 25 MVA 33 kV, then at new base values of 50 MVA 11 kV, our new per unit impedance it will be 16.2 per unit. There is one more equation. So many students get confused between these two, which is written like this: Z per unit is equal to Z in ohm into SB by VB square. So we can call this as equation number 2, and this is equation number 1. When to use equation 1 and when to use equation 2? Whenever two type of or two different set of base values are mentioned, and if it is asked to calculate a new per unit impedance value and old per unit impedance value is given, then we need to use equation 1. Whereas equation number 2 we can use if the impedance is given in ohm and SB and VB are given, we need to calculate the per unit value of impedance. So here there is no mention of two different set of base values. Here there is a mention of two different set of base values, and in this case equation number 2, the impedance is mentioned in ohm, whereas here impedance is mentioned in per unit. So be careful in equation number 1 and 2 when to use equation 1 and when to use equation 2. Question number 41 asked in ESE 2016. Stability of a power system can be improved by first using series compensator, using parallel transmission line, reducing voltage of transmission. So which one of the following statements are correct? Now just now we have seen that steady state stability limit is given by EV by X. In order to improve this steady state stability limit, one can reduce the X or one can increase the voltages. So in both cases, the steady state stability limit is going to be improved. Now how we can reduce the X practically? So one method, we can use the series compensator. So if this is a transmission line, it will have some reactance XL. So this is our original condition. And if we use the series compensation, means we are connecting a series capacitor with the line. So this is XL, original transmission line reactance, and we are adding a series capacitor. So here effective reactance, it will be XL minus XC. So here due to presence of XC, our X effective it will reduce, and if X effective is reduced, steady state stability limit it will be improved. So this option is correct. Using parallel transmission line, so that is also one way to improve the stability, but we don't use just for the sake of improving stability parallel transmission line because it will have more cost, but in order to have more reliability we use a double circuit parallel circuit line. So in this case, if this reactance is XL, this reactance is XL, then the effective reactance, as we know, it will be XL by 2 because both the reactances are equal. So parallel combination resultant will be half, so XL by 2. So by using this method also we can improve the stability. Another method, we can use the bundled conductor. So by using bundled conductor, X is getting reduced. If X reduced, stability is improved. That is also quite correct. Again, we can use fast switching breakers, fast action of mechanical devices in generating station like prime mover excitation system, that also improve the stability. So reducing the voltage of transmission, that is not correct because if we reduce voltage, steady state stability limit it will decrease. So this is not correct. So correct answer will be option 1 and 2, Roman 1 and 2. So that is option D is correct. Question number 42. A negative sequence relay is commonly used to protect. We know that in case of alternator there are different abnormal conditions. So one of the abnormal conditions for an alternator is unbalanced loading, and whenever there is an unbalanced loading, there will be a flow of negative sequence current, and in order to detect this particular condition we use negative sequence relay. So correct answer, it will be option A, alternator. For transformer, we don't use negative sequence relay. In case of transformer, primary protection will be provided by differential relay. For backup protection, we use overcurrent earth fault relay. Apart from that, there are different relays like Buchholz relay, then oil temperature, winding temperature, NDR, neutral displacement relay, and so on. For transmission line, we use mostly distance protection as a primary and overcurrent earth fault as a backup. For bus bar, we use differential protection as a main primary protection. So correct answer, it will be option A. What are the other abnormal conditions in case of alternator? So one is loss of prime mover, another is loss of excitation, and this is unbalanced loading. Now which relay is used to detect loss of prime mover condition? We use directional relay. To provide protection against loss of excitation, we use offset Maho relay. For unbalanced loading, as we have just seen, we use negative sequence relay. So these are all abnormal conditions that will take place in an alternator. Question number 43. In an HVDC transmission, the DC output voltage can be controlled to get inverter operation when the firing angle is for 0 degree till 90 degree. We can get a rectifier or converter operation. That is conversion of AC to DC. If you want inverter operation, then alpha it should be more than 90, less than 180 degree. For this condition, we will get inverter operation. In case alpha is 0 degree, then it will simply act as an diode. It will be simply a diode converter. So here, what is asked for inverter operation? So correct answer, it will be 90 degree to 180 degree. So option C. Question number 44. Consider the following properties regarding insulation for cables, underground cable. Low specific resistance, high temperature withstand, high dielectric strength. Which of the above properties of insulation are correct while using cables? Now in case of cables, we need to use insulation because the cable are laid under the ground, so there is no natural air available as an insulation. We cannot use the bare conductor. Similar to the overhead conductor, we use the bare conductor in case of overhead transmission. So here the insulation, whatever insulation we are using, it should have high resistance. That is the main thing. Then its dielectric strength, it should also be high. So if resistance required is high, its specific resistance, that is rho, it should be high. So this first option is not correct. High temperature withstand, that is the desired thing, because whenever current flows through the conductor, there will be I square R loss, and because of which there will be heating effect. So therefore insulation should withstand the high temperature. So this is correct. High dielectric strength, that is also correct. So 2 and 3 are the required properties. So correct answer, it will be option C. Question number 45. In a biased differential relay, the bias is defined as a ratio of. So this is asked in GATE 2006. Now we know that biased differential relay, it can be indicated like this. So this is the equipment that we need to provide protection. So here the incoming side and outgoing side. So here we are using the CTs on the primary side and CTs on the secondary side, and they feed to the relay which is known as biased differential relay. So this relay will have two coils. One is the restraining coil. So these restraining coils are divided in two parts. So this is NR by 2, half turns here and half turns of restraining coil here. And this one is our operating coil, NO, number of turns of operating coil. This terminal is connected to the ground. So this is a rough schematic of biased differential relay. So here the spill current or the current flowing through the operating coil, it will be I1 minus I2, and the current flowing through the restraining path, it will be I1 plus I2 by 2. And for relay to operate, this I1 minus I2 has to be greater than K times I1 plus I2 by 2. So here I1 minus I2 is the current flowing through the operating coil, which will tend to trip the relay, whereas this current I1 plus I2 by 2 is known as the circulating current, which will tend to restrain the relay from tripping. This K is nothing but the bias, and we are asked what is this bias. So remember, this K, it is a ratio of restraining coil turns divided by operating coil turns, that is NR by NO. So number of turns of restraining coil divided by number of turns of operating coil. So correct answer, it will be option A. And for which equipment we use this relay? So remember, this particular relay we can use for providing protection for transformer, then bus bar, then generator windings, and so on. This protection is also known as a unit protection, as it has a very clear cut zone of protection. It is known as a unit protection. It will operate only if fault take place within its zone. It will not operate for the fault taking place outside the zone. What is the zone for this? So everything that is covered within these two cities, so all these equipments will be provided protection against the faults. So question number 46. The transmission line distance protection relay having the property of being inherently directional is. Now for transmission line we use distance relay. So there are different types of distance relays like impedance relay, reactance relay, Maho relay. Out of these three, so Maho relay is the only relay which possesses the directional property. So its characteristic will look like this: circle which is passing through the origin. This is R resistance, this is X. So if impedance seen by the relay falls within this circle, then relay will trip, and outside this relay will restrain. Now if you observe carefully here, this particular path, it is nothing but the directional property. So here in this direction we can say relay will trip, and here it will restrain. So as it does not operate for the fault impedance in this region, so here relay is going to restrain, meaning is that it possesses the directional property, which is not true for impedance or reactance relay. It does not possess the directional property. So question number 47, asked in ESC year 2013. A 50 MVA 11 kV 3-phase generator has a stored energy of 400 megajoule. The inertia constant is. We know the formula for inertia constant H, which is a ratio of kinetic energy stored in megajoule divided by machine rating in MVA. So here how much is the kinetic energy stored? It is 400 megajoule divided by machine rating is 50 MVA. So this will be 5 8s are 40. So it is 8 megajoule per MVA. So correct answer will be option B. Here they are asked what is H, inertia constant. Question number 48. To equalize the sending and receiving end voltages, impedance is connected at the receiving end of a transmission line having the following ABCD parameters. These ABCD parameters are given. The impedance so connected would be. So what impedance should be connected at the receiving end so that sending and receiving end voltages it will be sent. So if you see here, so this transmission line, it can be represented by ABCD parameters. So here there is a sending end, and here there is a receiving end. The sending end voltage is Vs, receiving end voltage is Vr. So what impedance need to be connected at the receiving end so that Vs equal to Vr, that is asked here. So this Zr we need to calculate. So Zr equal to question. Now we know the relation between Vs and Vr. So Vs is AVr plus BIR, and we know that the condition that is given here is that Vs should be equal to Vr. So therefore we can write Vr equal to AVr plus BIR. So if we simplify, so Vr we can take common, so 1 minus A equal to BIR. So if you take a ratio of Vr upon IR, that is nothing but the impedance connected at the receiving end Zr. So that will be equal to B upon 1 minus A. How much is B here given? It is 200 at an angle of 90 degree divided by 1 minus A, which is 0.9 at an angle 0 degree. So we can write simply 0.9. So simplifying, so numerator 200 at an angle of 90 degree divided by denominator 1 minus 0.9, it will be 0.1. So that will be 2000 at an angle of 90 degree. As it is an impedance, it will be ohm. So ZR, if we connect 2000 at an angle of 90 degree, that is J times 2000, that is a pure reactance of 2000 ohm, then Vs will be equal to Vr. So correct answer, it will be option C. Question number 49. Which of the following buses are used to form bus admittance matrix for load flow analysis? Now we know that for load flow analysis, we need to consider all three type of bus. That is load bus, which is also known as PQ bus, then generator bus, which is also known as PV bus, or voltage controlled bus, and slack bus, which is also known as swing bus or reference bus. So all three types of buses we need to consider. So correct answer will be option D. Moving to the question number 50. Normally Z bus matrix is. Now whenever we are doing the load flow analysis, two type of buses we come across. One is Y bus, another is Z bus. So they are related with each other as follows. So Z bus is Y bus inverse. So it is a matrix. So Z bus matrix is inverse of Y bus. Now we know that in case of Y bus there are many elements which are zero, because there are many buses in a power system which are not directly connected. So therefore the reactance or the admittance corresponding to that particular line, it will be zero. So it contains many zero in the matrix. So this particular matrix is a sparse matrix. So what is sparse matrix? Matrix having many elements as zero is called as a sparse matrix. So therefore it is very easy to do the calculation in case of Y bus. But when we take inverse of Y bus, we will get Z bus, and this Z bus will not have the zero element. So it is the full matrix. That is difference between these two. Sparse matrix is Y bus is a sparse matrix, whereas Z bus is a full matrix. So correct answer, it will be option C. So always we use Y bus for load flow analysis. So this is preferred for load flow analysis, and for short circuit analysis we use Z bus. That's the difference between these two. So null matrix means a matrix with all elements zero. That is not correct. Sparse matrix, Y bus is a sparse matrix. Here Z bus is asked. That is not correct. Unity matrix means all the diagonal elements are 1 and off diagonal elements are 0. That is also not correct. So our correct answer it is option C. Thank you.